Okay, good afternoon, everybody. We are ready to start. I have some communications to deliver to you before we start with the lecture. First of all, I want to remind you how to mark your attendance today. And remember that you have a link to an Excel file shared. The link can be found by going on Virtuale. In Virtuale, under our page, the page of Science of Climate Change and Climate Action. Sorry if I repeat it, but I think this is extremely important also for those who are attending online. So you have to go to News, and on News, there is this discussion. Science of Climate Change and Climate Actions is the only one for now. And here you can find the link to the spreadsheet. If you click here, you get to the spreadsheet, which is somewhere, just 1 second, here.
Professor, could you please share your screen?
Yeah, sorry, I apologize. Just 1 second.
Thank you.
Yeah, sorry for that. So this is now shared. So you see under Virtuale, there is, I go back 1 page. It's in Virtuale, in the page of the course, which is this one. You have to click on News, and then you get to the forum page. Click on the only one post that is visible now, and there is the link to the Excel spreadsheet, which is here. So you see a list of matricula numbers, ID numbers. You should find yours. If it's not there, you go at the bottom of the Excel file and you put your ID number, and you can mark your attendance on today's lecture. The lecture, as I said, the attendance is recorded midnight of the day the lecture is given. So you have to mark your attendance by today. Once it is recorded, the column with the date, today's date, is removed. And it's not possible, I am afraid, to go back and mark your attendance for the past. You understand easily why, okay? It's not a problem. You are not required to attend all the lectures. You are only required to attend 70% of them. This is not my rule, it's a rule by the university. And so it's not a problem if you miss the first one. But of course, be careful, because if you miss more than 30% of the attendances, you will not be able to subscribe to give the exam. You can still continue to attend the lectures, but at the end of the lectures, I have to communicate to the university the matriculas of the students who attended 70% of the lectures. And if you are not there, you cannot subscribe to the exam. And I'm sorry, I'm not the person to whom you may complain if something happens, because if at the end I don't see enough attendances, I have to defer you to the offices of the university, to your student secretary. I hope it's clear, so please mark your attendance. Second communication. Unfortunately, I'm sorry I'm not able to deliver good news. As I promised, I investigated with the university whether I am entitled to fix an exam before the end of the semester, and the reply was no. They said you are allowed to schedule an exam only starting from June 10. I'm sorry, I am monitored. I cannot make an exception. I cannot, in a way, hide behind a curtain and make the exam to you without telling anybody. You understand? If I fix an exam, we are getting about 100 students, the first one, and so it's not possible to make anything behind the scene. And as I said, the scores, given the high attendance, is monitored. So I'm sorry for that. But I confirm that I will fix 3 exams before the end of July, and another one in September, and other 2 exams in January, end of December, January next year. So this is still my plan. I am also required to schedule 6 exams, so I will do them for sure. Maybe even a 7th one if you need it, but I cannot make any exam before June 10. Sorry for that. Okay. I think we are now ready to start with our lecture. And as you may remember, under my website or under Virtuale, there is a list of links which we more or less follow. As I said, some more links may appear later on, some of them may disappear, and also the order may change, depending on how long it takes each lecture and other issues. So today, I would like to start an introduction to climate change and to explain to you the issue, the climate change issue, and some evidences of climate change. This will occupy this discussion a significant part of our course together, because as I said, we have to understand what we are talking about before talking about science, which means the theoretical basis for solutions, and before talking of actions. We have to understand the orders of magnitude, what is going on, what we think will happen into the future, and then we can start talking about actions, which means solutions. Okay, so let's click on the climate change problem. And here you see that there is a long lecture, not really long, but a lot of text. Let's focus on the PowerPoint, which you can download at the end of the story. And as I said, the PowerPoint is useful for you to follow on the screen. Just 1 second for the download. It's here. And here is our PowerPoint. So, climate change. Climate change, you know, is an extremely topical issue, and this is why this soft skill course is so popular, because as we mentioned last time, it's a global issue, it's a global problem which involves several spheres of the human knowledge and several disciplines. Climate change means, first of all, monitoring climate change, monitoring climate. It means the science of it, and it means solutions, because it's a global issue which is tightly related to sustainability, and therefore we need to take action, as we well know, because the matter is frequently treated by the media, frequently discussed by several information channels, frequently discussed by international organizations and politicians. It ranks very high in the agenda of several countries nowadays. So why it's so important? First of all, as I said, it's tightly related to sustainability, which sustainability, you know, it's another relevant issue. I would say it's a comprehensive problem, which involves climate change. It involves sustainability of our societal development, because sustainable development means a strategy for ensuring that our societal development is optimized without delivering no negative impact, absolutely no negative impacts on the future generation, which means that our use of natural resources should be made in a way that we grant the right for future generation to profit from the same opportunities. So we cannot exhaust natural resources like energy, water. We cannot exhaust because we have to grant to the future generation the right to profit from the same natural resources, from the same natural environment. This concept of sustainability is relatively new. You are younger than me, fortunately for you, which means that you don't have memory of what were the global problems in the mid of the previous century. sustainability was not considered to be a problem at all. In the mid of the previous century, the problems were related to the industrial development, to recovering from after the Second World War, and only towards the end of the 60s of the previous century, we started to realize that our rush to development, the great acceleration, was producing negative impacts on the environment. And the first thing that clearly emerged, became clear, was water pollution in rivers, lakes, oceans. And water pollution emerged as a problem depending on the location. In the United States, at the beginning of the 20th century, the past one. In Europe, around the mid of the century, in other countries later. And also air pollution was another problem, which clearly emerged soon after the Industrial Revolution. It was clear in the urban areas. Air pollution started to become a big problem. And there were also other societal problems. But if we consider the global issues related to environment, this is the timing when we realized that there was a problem. To give you an example, water was considered to be an infinite good, an infinite resource up to 1968. And in 1968, the European Chart for Water was written and was approved. In the European Chart for Water, there is written there that water is a finite resource. Up to that time, we didn't care much about water. Water was considered to be infinite, at least where it was available. Of course, the communities tried to settle down where water was available, and then it was considered granted for sure. But then after the pollution, after the soil pollution, which meant that also groundwater became polluted, we started to realize that water had to be protected. And we realized that water was finite. It was an innovative concept, a very innovative concept. Why? Because you have to consider then that when you admit that something is finite, you have to give a value to it, and an economic value possibly to it. In fact, today we pay for water. We pay for our drinking water, for the tap water. We pay a fare that is controlled, controlled by authorities. Water is still considered a public good, but we have to pay for it because we admit that it's finite. Also, we pay for distribution, but the main reason why we pay for water is that we accepted that it's not an infinite resource. It was innovative because you may think that this is something like why we didn't realize it before. But I propose to you an analogy. Think of air. Air to breathe is considered to be infinite, which is okay. It means that we are free to breathe without paying it. Can you think of a time when somebody realizes that it's not infinite? This would be something really shocking, you know? And so I hope that this example helps you to understand that even when water was recognized to be a finite good and people had to pay for it, this was shocking. It was a huge innovation, but at the end, we recognize that it is a good solution. It is something that, a controlled administration of water, a controlled fare for it, we realize it's a good solution because when an economic value is associated to a resource, you respect this resource. You don't waste it. You realize that it's important. And also it allows to manage it in the best way. Otherwise, if we wouldn't pay for water, how could we sustain the expenses for reducing leakage, for instance, or for desalination? Because in the future, we are talking about desalination, because it's clear that in the future we may have some water problems. I mean, important water problems, and the solution is clear, it's the sea. As we will see, in the sea there is plenty of water for everybody, for any possible solution of societal development. But on the other hand, desalination is costly. And it's also impacting on the environment, but let's forget about it for now. And I hope that you understand that these funds that we recover from paying water serve us to save water. It's not a matter of making a commercial use of it. Of course, there must be a legislation that avoids a commercial use, but once that the legislation is correct, is equitable, and it's respectful of the human rights, then that's fine, that we pay for saving an important resource. I anticipate that more or less applies, the same situation applies to climate change. If we want to move forward with the mitigation of climate change, adaptation of climate change, we will have to pay for it. And it's a societal cost, which is very relevant. It's huge. It's huge. On the other hand, once that we pay for it, we probably would better understand the need for action, the need for making our best to make this expense to avoid climate change. Evidences of climate change. This is a long story, and I think it is interesting to go through it. I mean, we can look to glaciers. There is a figure here. There are several figures related to glaciers retreat. If you go to our world in data, the link that I suggested you last time, there are plenty of data about the glacier extension, Arctic ice extension, and progress in time. And you see that there is a reduction in time of the extension of the ice caps and glaciers in general. There are some spots in the world where there is less temperature increase, and therefore glacier retreat is not so evident. But in general, the pattern is glacier retreat, which a very impressive pace. You see the figures from 1900 to 2015 after 100 years. Of course, it's not easy to compare to pictures because it depends on the season, many things, but still you see that the difference is striking. Another example, which is probably less striking, is the graph that you see bottom right, not bottom right, but bottom middle, this black and white graph here. And this is a graph of the annual minima of the Po River at Ponte Lago Scuro. Ponte Lago Scuro is close to the mouth of the Po River, close to the estuary, actually. We should talk about the estuary. You know that I am an hydrologist, so I frequently make examples regarding water. So sorry for that. It's a little bit of a bias, but I will make an effort to make also other examples. So this is the annual minimum of the Po River, which shows that a long time there is a slight decline. Minima means I pick up the day with the minimum flow, minimum volume of water flowing, and I put it over the graph. And the record starts from 1920. Actually, there are reconstructions that go back in the past, but let's stick on this data. They are observed and therefore quite reliable. Okay, when you look at data about climate, about environment, the reliability of the data is an issue. Uncertainty of the data is an issue. But in this case, we can safely say that for the general pattern, the data are reliable. So there is a slight decline, and especially if you look at the recent past, and this is up to 2009, and the situation didn't improve in the past 10 years. I would say that it's worsened a little bit. Last year in 2022, I think I already mentioned to you, we had the worst drought in the history of the Po River that we know. And if we go back 200 years, this is the history which we can say we know. It's not reported here. Here it is only 100 years, but we can reconstruct the data for 100 more. There is no similar situation in the past 100 years. compared to now. So the situation that we have now, that we had in 2022, which is still continuing. Last week, you probably heard from the media that the drought in the north of Italy and Europe is continuing. So the situation that we have now is unprecedented in the history that we know. But this graph also allows us to note that there is some variability. We already discussed about variability, change and variability. There is variability. So we can see that if we look at droughts, there were other droughts in the past which were striking, which were a bit impressive. And this poses a problem because, of course, we have to recognize whether the current situation is given by variability or change. And this is a big scientific question. The upper right picture shows water balance for the Po River basin. Water balance means that we take the input which comes from precipitation, and then we see what part of precipitation goes in the underground and what part goes to the sea, and how much of it is withdrew from the underground. Groundwater withdrawal is significant in the developed societies. We see what is the rate of evapotranspiration, evaporation plus transpiration. And we see a couple of things in this picture that are emerging. First of all, let's consider as a premise that the Po River Basin is an area where it is produced 60% of the gross domestic product of Italy. So it is extremely important. So these water fluxes are feeding in an area that is extremely important in terms of agricultural production, industrial production, and society in general. So if there is a kind of hiccup, if there is a perturbation in these fluxes, the societal impact is relevant. And we are talking about a volume of water that is really impressive. You see 78 billions of cubic meters of water every year fall in the form of precipitation over the river basin. So this is the first consideration. I mean, it is something that is societally very relevant. Second consideration, what you see here is a balance of water, a balance of volume of water. And it is a mass balance. It's a conservation principle. This is the way we study climate and other natural processes, by imposing conservation of matter. Can be conservation of mass, can be conservation of energy. In general, this is the principle. So when you hear about conservation laws, this is what we mean. For an engineer, it's probably a well-known concept, not for all of them. And for other disciplines, it is an important learning. So this is the way models work. Conservation of matter including energy. Because what moves, what fuels this exchange, these flows, it's energy at the end of the story. Maybe energy in different forms, electrical energy rather than heat. For instance, evapotranspiration is fueled by the heat. And of course, if we want to understand how the perturbations are affecting the system, we have to look at these conservation principles. How many principles do we need to apply? It depends on the number of things that we don't know, on the numbers of unknown. If we have several unknowns, we have to apply several conservation principles. Good. Now, I talked about variability of climate. So let's step back to this important feature. Variability of climate, you have heard of it. It's also called natural variability. Natural variability implies, as I already outlined last week, that the climate is not constant. And fortunately, it's not constant, because otherwise, with a constant climate, I mean, there will be less diversity in nature. So the variability of the forcings, the variability of the stresses, it's a good thing, because it enhances, it improves diversity of the natural environment, it improves its strength, what is called resilience. What is resilience? Is the capability of a system to recover from a shock. And how a system can become capable of reacting to a shock? By training. It's clear, okay? By training. So variability of climate is the very reason why nature exists, which is fine. It's something that is natural. So this means that even if we didn't have any climate change, any human-induced climate change, we would anyway have to react to shocks due to natural climate variability. Like floods, they always occurred in the past. Always. Drought, they always occurred in the past. On the other hand, there is, as we said last time, the feeling that the impact of human activities is worsening these shocks. How can we find a solution then? First of all, we need anyway a solution. This must be crystal clear. So now we are today here to discuss about climate change, but hadn't we had any climate change, I would be here anyway to teach to you how to adapt, how to mitigate climate shocks. So this is part of the human history. Humans had always to adapt to nature, to fight in a positive way, but it is a fight against the shocks that sometimes nature exerts, hits over us. Okay, this is something that is anyway needed. I mean, we have floods, we always had floods, and humans had always to find a solution to protect themselves against floods. And this need is today much more important because the human population is increased. We have more people exposed to these risks in larger areas with respect to the past. And we have a concentration of population in the cities, which means that we are more exposed to natural risks than in the past. So this is something, finding a solution to cope with climate extremes is something that we anyway need. And let me say, it is astonishing in a way that we continue to be got by surprise by these extremes. Okay, it is something that it is really puzzling, amazing, because we shouldn't be get by surprise, because our history I mean, it's full of these shocks. And today we also have the awareness that something is changing with respect to what is natural. So it is a little bit amazing that we don't get prepared. Why is that? We could identify several reasons, but I would like to mention to you a couple of reasons, actually. First, the fact that our memory of disasters is short. and this is proved. There are scientific studies that have investigated that the memory of a disaster lasts for about one generation, 30 years. It is proved that when people live in an area that is exposed to natural hazards, if for 30 years they don't get any occurrence of such natural hazard, then they try to forget about it. This is something that can be explained with the will of improving our situation. I mean, adapting and mitigating the impact of natural hazards means spending money, means spending resources, employing resources, means a limitation to our development. This must also be clear. If we want to limit climate change, we have to put a limit at our development, to the sustainable limit, which means a limit anyway. And this is something that is difficult to be accepted because we want to improve continuously, which is fine. We want to give to the future generation a better future. This is fine. And then we try to forget what are the principle of prudence, of care about natural hazards. This is one first reason. The second reason, in my opinion, is precisely the societal cost of it. And adapting to natural hazards, mitigating natural hazards requires an investment of resources, which is once again limiting our development. And therefore, for the same reason why we forget our memory, for the same reason we try to, in a way, to assume that these things will not happen again, at least for the time frame of our life and the life of our next 2-3 generations. There are studies on that. We tend not to care about what's going to happen after 3-4 generations. This is why climate projections are pushed forward up to 2100, because after 2100, people may not care much about what's going to happen. There is a third consideration, which is related to the type of institutional arrangement of countries. Democracy, which is, widely diffused today, implies that the long-term vision, the long-term vision into the future is somehow not considered, because the term of the politician is short. It's not a lifetime term. Fortunately, our fathers and mothers fought for it. No, so the term is short, maybe 10 years, but it's a term that is short in democracy. And therefore, there is the problem that, to look after the end of the term of the politician requires a forward-looking vision, which is not always recognized in democracy, because democracy means that you have to build your popularity, you have to gain the trust of people, and it is very, very difficult to gain the trust of people in the benefit that a given politics will achieve in 30 years from now. Usually people look at the short-term benefit because it is something that is more tangible, And in my experience, I realized that several times we want to have a transparent discussion about climate change. Transparent discussion means that there is controversy, and very often the solution to the controversy is to do nothing, because it's a conservation principle. When people really are concerned about the future, the natural reaction is to be conservative, to keep the status quo. And this is understandable. I really believe in transparent discussion, transparent decision making. But on the other hand, I realize that sometimes I would hope for a top-down decision by a politician that takes the responsibility, that pays for it in terms of maybe personal visibility, but this in some cases would allow a timely decision, which sometimes it's not possible, and for climate it would be really needed. Anyway, I think you understand now why climate change is a problem. It's a problem because it's important on the one hand, is caused by activities which it's not easy to change. It's caused by food production, it's caused by energy production. Climate change is not caused by the bad will of one person. It's not caused by the fact, it's not only caused, of course, it can be the bad will of one person can give a contribution. But the big change that we have to make if we really want to advance in fighting climate change is a change in our productive system, industrial system, and agricultural system. This is the big change that we need to make. And of course, good political management, good involvement of the citizens, and goodwill of each one of us in order not to use the car when we can't, when we can avoid it, etc. In order to limit our traveling for vacation, not to take the plane. This is how we can contribute. But the overarching issue is our productive system. So you understand that if you talk about changes in the agricultural system, if you talk about changes in energy production, it is an issue because these changes, first of all, we realized in the past 1 year that when we talk about energy, there is a relevant cost associated to it. And therefore, making a change means that the bill may be doubled or even tripled. So it's sensitive. And also, you know, when it's time to discuss, keep in mind that any change that you make to the system has an impact. So if you want more water, you have to build a dam. The dam has an environmental impact. And the dam in turn has an impact on climate change. So it is important to assess the pros and cons. And when you discuss the pros and cons of any solution, the discussion becomes tricky, interesting, let's say. So we already talked about weather and climate. And let me, so I'm not insisting on the difference between the two. Let me now make an example of an effect of climate change. And here in the graph, you see temperature on the average over September during 10 years in several cities of Japan. And you see that there is an overall increase, but there are some cities like Tokyo, where the temperature, Tokyo is the yellow one, increased a lot more. And you see in general that in the cities, there are different paces of warming, because there is the superimposition of global warming and the heat island effect. I think that you heard about the heat island effect. It is something new, because up to 50 years ago, there was no discussion about it. We realized that it was an issue starting from the end of the past century, or maybe 1980, but really it has not been an issue for a long time. Now it's an issue because in the cities, you know, we warm with our buildings, and there are many reasons why the weather is hotter in the cities. Why I am saying this? Because climate change, it's not uniform. We already, and climate is not uniform, we know that, but also climate change is not uniform. We already mentioned that the southern hemisphere is warming less than the northern hemisphere. And let me just say cities are warming much more than the surroundings. And for a different a different phenomenon, different process. It's not CO2 emissions in the city. It's not global warming. It's, as I said, warming of the buildings, air conditioning, and also the fact that the urbanized areas reflect the solar radiation more than the natural areas. They absorb less heat, they reflect more, and therefore they contribute to the heating. This is a big issue because most of the relevant percentage of the human population lives in big cities. And therefore, even if it's a local effect, it's extremely important and is causing this effect a lot of death, especially in the countries that are less equipped with air conditioning and with other solutions for mitigating the extremes of climate. So let's be aware of that climate change is a global problem with local impact. And the solutions are not a uniform recipe. We must adopt different solutions and study different science depending on the context. Okay, let's move forward. So climate change. What is climate change attribution? And now we are trying to explain more reasons why climate change is a debated issue. It's a controversy. Attribution means that we try to understand whether climate change, what is the reason for climate change? What is the scientific explanation? And I put the accent on the word scientific because we have to try to be objective. So we have to understand what is the cause of climate change. Why are we so interested? One may say, okay, I don't care about the cause, I only care about solution. Okay, this, for an engineer, it's a good reasoning, like let's give the task of finding the causes to researchers. I am an engineer, I want to focus on solutions. But actually, the solutions depend on the cause. If we want to identify a good solution, we have to first understand the causes of our discomfort. So again, let me talk about floods. Why a river is flooding? Is flooding for climate change, or is the river flooding because of deforestation or urbanization? It would be interesting to make a poll of that. Like, what is your opinion on the relative weight of in flooding of climate change, urbanization, or deforestation? Of course, if the cause is climate change, the solution is different. Okay, you may say, I build an EV and that's fine, whatever is the cause. On the other hand, there is to say that yes, there are some solutions that are have a general validity. Other solutions, like for instance, de-urbanization, de-cementification. This is useful if the flood is significantly caused by urbanization. Or reforestation. Okay, let's just focus on flood. The reforestation is a good thing if we like the forests, if we like the natural environment. But in terms of flood, reforestation is a good investment. So you understand, you have to identify the causes, and therefore attribution is relevant. And attribution, as I said, means science, means understanding the processes. The problem is that when it comes to the question of how much is significant the human contribution to climate change, how much is climate change is due to human activity, it's not a yes/no question. If it would be a yes/no question, there is a clear answer. Yes, human activity is impacting on climate. If I had to select between yes and no, I would put without hesitation a yes. Okay, but if then I have to give a number, like how much human activity is impacting on floods in Bologna, and look, I need to refer to a context because the impact of climate change is local, but I can also avoid to refer to a context, like, let me make a provocative question. With respect to global warming, how much is human activity contributing to it? 20%, 40%, 60, 80, or from 50 to 100, from 60 to 80%? It's not easy, because if you look back at the glacier retreat, we will discuss again about it. It started in 1750. So 1750, you know, before the Industrial Revolution. So it's clear that there is a natural component in this warming. At least at that time there was. At the beginning of this retreat, there was a natural component. But now it is without any doubt that there is a human component, but if you have to give a percentage, it's a problem. And it's a problem also in the scientific community, because there is a huge debate on that. And this is why, in view of the global relevance of climate change, this is why it is a controversy. And there is a Wikipedia page which is called the Global Warming Controversy. It's still continuously revised. You can look on that, and there is a clear description of what is the controversy about. The controversy is not about, are we warming? Yes, there is no controversy, we are warming. The controversy is not about, are the human influence on that? Yes, the humans are. The controversy is about attribution of single events or attribution of weight to different causes, because there is for sure an integration of drivers. There are several drivers. But of course, if we look at the progress of temperature, you see the figure on the upper right, there is clear evidence of warming. And with hot spots, you see that warming is not uniformly distributed. And there is the date in the bottom of the figure. It is too fast, actually, but it is going from 1950 through the end of 2013. And I mean, it is clear that we are warming. It's clear that we need to be prepared to something. We need solutions. What are we discussing in this course? We are discussing here about this controversy, but we are discussing on the science of it. And we are not discussing, I already mentioned this, I think, last Monday. We are not discussing about the politics. We are not discussing about communication. Let's try to look at the evidence. Science should look at evidence. Okay. When did we become aware of climate change? Well, earlier than you could expect, because already at the beginning of the 19th centuries, people noticed that glaciers were retreating. As I said, they started to retreat in 1750. And therefore, already at the beginning of the 1800s, people noticed that. And also, people noticed that there were geologic remains, geologic witnesses of different climates in the past, a different climate in the past. And already in the 19th century, when air pollution became an issue, the Industrial Revolution is around 1850, 1880. It was the 19th century. And air pollution was already an issue at the end of the 19th century. And people realized that the air pollution was causing an increase of temperature. Close to the industries, they realized there was an increase of temperature due to probably they assumed, due to the fact that the dust in the air was trapping the heat emitted by the Earth's surface by radiation. Was trapping. They understood the first basis of the greenhouse theory, of the greenhouse effect. And So they outlined, as you can read there, for the first time, the scientists, that emission of gases and pollution by humans could alter the climate at local, but also at global scale. And during the 1960s, this evidence became striking. It was clear that carbon dioxide and greenhouse gases in general, because it's not only carbon dioxide, were giving a contribution to Earth's warming. And also, but you have to also to be aware of the fact that around the mid of the previous century, around 1960s, the scientists also pointed out that this pollution, this air pollution, could, in some regions, provoke a cooling effect. In fact, if you look on Wikipedia about the global cooling, there is a Wikipedia entry called Global Cooling that explains what was the reasoning behind this. And indeed, they have identified this evidence of cooling effects as the result of the emission of a particular greenhouse gases. I think it was an aerosol. I don't remember what kind. You have to look at the Wikipedia page. And okay, here, global cooling was attributed to orbital changes and increasing human emissions of aerosols. I remember well. And however, the concept of global cooling disappeared when it was clear that after the 1970s and during the 1980s, the global temperature was increasing. Okay, this is a very brief history of climate change, and let me move forward with the rising temperature of the 90s. And during the 90s of the past century, there was an increasing awareness. Books were published and scientific papers flourished on the global impact of increasing CO2 concentration. And you know that due to the great acceleration, CO2 concentration increased about 25% at the global level from 1980 to today. So, of course, this was monitored, and climate change became an increasingly concerning issue up to about 20 years ago, when the controversy and the debate assumed a central role also from a political point of view. But the climate change issue started to rank high in the agenda of politicians about 15 years ago, so not a long time ago. And more and more in the past 5 to 10 years. Okay. There is too much in this slide, but let me just try to summarize it. So we have to talk about science of climate change. And I already outlined last week that it's an interdisciplinary effort. It's an interdisciplinary science because it involves atmospheric science, hydrology, so water cycle science. Also, it involves soil sciences, geology. And it is a very active field of research for the reasons that we already discussed. The fact that it is interdisciplinary, I think it's an added value, but actually today is still a problem because communication between different scientific disciplines is not easy for several reasons that we don't discuss here because we are not interested in that. But really, everybody advocates interdisciplinarity, but only in a few cases we can really achieve it. We can really achieve a productive dialogue between scientists of different disciplines, which use different languages, use different conservation principles to describe their processes, use a different symbology, different math, publish on different journals. And you may think of something like What's the problem? I mean, if one publishes in Nature and another one publishes on a journal on medicine, what's the problem? You may think, but actually it's a big issue because academic assessment of productivity of excellers is based on bibliometrics, is based on the counting of scientific papers. For instance, you may have heard that 97% of scientific contributions agree on human-induced climate change. Is a ill-posed statistic, because we should say something more on that. But the problem is, how do you define a scientific journal? For instance, journals focusing on hydrology often are not included in this selection of papers because hydrology by some scientists is thought to be not relevant. And again, academic assessment means funding, means resources. And you may think of something that is dirty, that is, I mean, not good. A scientist, we may say, should not work for seeking resources, for seeking funding, but only for seeking the truth. Okay, that's true. On the other hand, without funding, a scientist cannot work at all, because a scientist needs to survive. A scientist needs students, needs to promote students, to promote knowledge, needs to publish, and publishing costs a lot of money. So basically, there is a kind of fight for survival also in science, which is fine, because science is must be based on competition. It is perfect. But on the other hand, this competition undermines the dialogue. And this is a problem for the scientific community. And then there is the problem of communication with policymakers, with politicians. It's not easy. And even if we try to establish formal channels for communication, then very often the communication between science and politics takes place along channels that are unconventional, because they may be more efficient. So, for instance, the connection between the academia and politics is weak in several countries. It is stronger, the connection between research centers, maybe also private research centers, and politics, because this is more efficient. Why it's more efficient? Because if you manage private money, you have less constraints than in managing public money. Public money, we need constraints. We cannot be free to manage public money as it was our own money, because if we manage our own money, we take the risk of a bad management. If we manage public money, the risk goes to the public. So we must have constraints. I recognize as a public employer that I appreciate constraints on my activity. On the other hand, constraints means that the communication may become, and the management of research may become less flexible. So there are several problems that, I am very positive. It's not bad will. In some cases there is bad will, but if a system, a democratic system, a scientific system works in a certain way, and it's the cause of inefficiency very often relies on the organization of the system itself rather than in one person that is making authoritative decisions. Anyway, what is another problem that I want to point out? The role of engineering. Engineering is, when we mention the word engineering in the context of climate change, usually the reaction is a disappreciation, because engineering is attributed many of the faults when we talk about climate change, environmental impact, of course, because it's the role of engineer to design dams, to design urbanization plans, to design buildings, and all of these interventions have an impact. And therefore, today what we see is that the role of engineering in climate science, where I talk of climate science in a very broad sense, it's very low. Engineering is not much considered for the reasons which I just mentioned. This is actually a problem, because if you want to design solution, it's engineering that is in charge of designing solution. It's engineering that knows the methods and the solutions that can be applied. So this is why in my web pages you can find a section dedicated to the distrust in engineering. This is a problem in seeking solutions to climate change. There is a distrust in engineering, and there is the tendency to undervalue the solutions proposed by engineers. Maybe that engineers have their rate of fault, their faults, for sure. I mean, I'm not saying that it's just a bad will by the other scientific disciplines. On the other hand, this is a problem. And there is, for this reason, also in my web pages, a box that explains the role of engineering in sustainable development and in devising solutions for sustainable development. I will talk about engineering. We don't have much time really here to discuss about the specific, the technical details of solutions, but I will take the opportunity to talk again about engineering, which is better explained here. Okay. Okay, there is not much that I have to add related to this first three paragraphs, but let me focus on the bullet points. And the bullet points give some examples of open questions, open research questions related to climate change and science of climate change. An introduction. When we talk about science, we talk about unknowns, because otherwise there would be no science. Science is the investigation of natural processes to improve our knowledge. If our knowledge was already perfect, we wouldn't need science. Actually, today we recognize that we need science. There is still some debate what kind of science we need. So even the founding agencies that are in charge of founding research, founding science, they often discuss about their programs. What kind of sciences should we need? The pandemics brought to our attention that we need more research on global health problems, on viruses, vaccines or not, but still the pandemics clearly gave some priorities, shifted some priorities. So it is an interesting discussion, what kind of science we need. And an interesting discussion is, should we dedicate substantial fundings to blue sky, the so-called blue sky research, or applied research? What is blue sky research? It's fundamental research. Or should we focus on applied research like engineering? Or let me make an example that is less extreme. Should we focus on basic science like mathematics, or should we focus on applied science like ecology? This is an interesting question, and it is also called blue sky research. And what is how do you make a difference? How a founding agency can make a difference? This is an interesting question. You may say, what is the interest with regard to climate change? Well, the interest is clear, because we said that we need science in order to better understand how nature works, and the decisions by founding agency can really drive science. So An interesting question is, should funding agency fix a target and deliver the funding basing on achievements? So should we set, when planning our research activity, milestones and deliverables? And should the money be given after we deliver the deliverables, like the National Recovery Plan? The National Recovery Plan works in this way. You make a research proposal, you set a deliverable. Once the deliverable is delivered, then the money is given to the researcher. Or should we just tell the researchers, feel free to propose your own research program, and we give to you the money basing on a preliminary assessment of your idea? What's the difference? The difference is that in one case you say, tell me what solution you are delivering to decrease the temperature in big cities. In the first case, it means applied research. In the blue sky research, the same problem may be formulated according to this statement. Give me an idea for improving our knowledge about the warming in big cities. And therefore, you elaborate a proposal like, I propose to measure, to monitor the process by collecting this data. I will explain the data with this model. This model will give you a prediction that allows you to study the solution. And then it's evaluated, and if it is successful, it is funded. And the money is given on the basis of the idea, not on the basis of a solution that is delivered. This is extremely relevant. Extremely relevant. Actually, in Europe, it works that in a way that we researchers are required to set deliverables, but there is one funding agency, which is the European Research Council, that delivers funding for blue sky research. And the European Commission is debating what kind of, how much funding to be given for blue sky research, how much funding is to be given for applied research. You may think that giving too much freedom to a researcher, it's not a good thing, because it's not a good move, because we need solutions today. So better to give money for solution rather than giving money for ideas. On the other hand, history clearly, we learned from history clearly that the creativity and in the arts, and in science is the best creativity is obtained when you give freedom to the researcher, to the artist. So nobody asked Leonardo, or maybe that somebody asked Leonardo to paint the Gioconda, but actually we think that it was a spontaneous decision, maybe that they have commissioned the painting, but how to paint it was a decision by Leonardo. Otherwise, it's a bit of a problem if you ask to a musician to compose a melody without without allowing creativity. Everything would be standardized. Okay, let me go again to the bullet points. Research questions that are open. It's interesting to discuss about them. The interaction between human-induced climate change and natural climate variability, already discussed, okay? Which is varying from context to context. Uncertainty assessment of climate simulation for the sake of engineering design, it's a different story. We already mentioned that. If I talk about uncertainty in communication is one thing, if I talk about uncertainty in technical design is another thing. In technical design, unfortunately, we are a little bit behind. So very often the engineer is left with the question, how can I estimate the future climate? How can I get this number? Future rainfall, future warming. It's not easy. Okay, for communication, it's a little bit easier because we can say several researchers agree that this will happen. But if you go for the design of a dam, unfortunately, this cannot be, it's a method of communication, it's a method for decision making that cannot be adopted. I cannot say I design a dam based on consensus. I ask several engineers and what should you do? What should I do? What should I do? And then I make a plan. No, absolutely not. It is something that has to be designed on the basis of an objective information of uncertainty. The capability of climate simulation to reliably reproduce the frequency of extremes. This is a big problem. So one thing is to predict how the climate will evolve on average. Another thing is how the extremes will evolve. And why it's more difficult? It's quite obvious. Extremes are very rare. They are not something that occurs every day. It is relatively easy to predict something that occurs every day. It's not easy to predict something that occurs once in 1,000 years. But this event that occurs once in 1,000 years, if it occurs, it's a disaster. So we cannot just forget about it. This is what usually happens. When we make planning, engineering design, we tend to forget about the very, very rare extremes, because first, we don't know how to handle them. What should we do with something that is very rare? How can we estimate this number? First. Second, getting protected with something that is very rare requires a lot of money, which produces a benefit once every 1,000 years. So who is willing to bet on something that occurs every 1,000 years? Nobody. So we tend to forget about it. But actually, we realized recently that we got several occurrences of events that in the past we thought that would be impossible. And now we got some of them as a sequence. So this is an indication of something changing, but it's also an indication that we shouldn't forget about something that we think it's very rare. Are we now planning for an earthquake of magnitude that has the capability to completely destroy Bologna? No, we are forgetting this event because we think it's impossible. But what if it occurs? This is something, extremes are still something that, as an engineer, I tell you, when I have to reply to the question, which is becoming more often and often and often, like what's going to happen in terms of water scarcity in 2050? My God, how to reply to this question? I already anticipated the next point. These so-called, I use the term impossible event, are also called black swans. Black swans means something unexpected. And there is a nice, if you go on Wikipedia, there is an entry of black swans because these are an issue. It's something unexpected, which occurs more often recently. Tipping points, I think we already discussed about tipping points, correct? I already discussed about tipping points last Monday. Yeah, perfect. Thank you to somebody who nodded. Okay, and estimation of design variables, which is more or less the same as making prediction for technical purposes. Design variable means it's a bad translation from Italian to English, means design event. Because in Italian we say variabile di progetto, which means the number that you use to size something like a building or a bridge or a riverbed or a river or a flood protection. And I translated in design variable, but it's a bad translation. Some colleagues pointed out to me that it's a bad translation, but I hope you understood what I mean. Okay, tipping point we already discussed, so let's forget about it. And this slide was already shown, so let's forget also this one. Oh, this is very interesting. Climate data. Exciting, very exciting. So science is based, as I said, on observation and on testing. Testing means testing a theory against evidence. Evidence means data, means observation, means numbers. And there are several data which refer to climate. So we often talk about temperature, but it's only one. We could talk about rainfall, snowfall, soil moisture is also climate data, and several others. And also climate data is also the percentage not the percentage, is the distribution of land use, is a data that is tightly, very closely connected to climate. And as I said, we need this data in order to perform our experiments. What is the problem? The problem is that we don't have much data. We don't have long records. We don't have many records of climate. I think I mentioned this last Monday, and sorry, I'm teaching 2 courses focusing on climate change with some overlap, and therefore sometimes I may run the risk of confusing what I say in a course and what I say in another one. But I think I mentioned to you that we have the problem that temperature, the observed period of temperature is short, starting from 1850. And of course, when you talk about climate has a time scale that is very long. So 200 years of data is nothing. And this is a relevant limitation indeed. Also, for some kind of climatic data like rainfall, it's even shorter. River flow, it's even shorter. Think that water engineers, one of the most challenging questions is to estimate how much water is available from a river, how much water flows into a river, because there are very few rivers that are monitored. For other rivers, we have to invent something, like making a comparison. I look at a river that is monitored and I make a comparison between gauged and ungauged rivers. So it looks like a stupid question, but actually we don't know how much water is flowing into a river, and we don't know how much water is underground, how much water we can withdraw in a sustainable manner from the underground. So it is very interesting. It is very interesting because we have to really devise ideas for improving our knowledge of the processes. And this is curious. If we look at the longest records, if we look at the country where observation in general, with very few exceptions, started first, this is Italy, probably because of its long history. But there were also other civilizations, ancient civilizations, that didn't start so early as in Italy. Not very early. In Italy, we started around 1600 to make the first observations of rainfall. And a curious thing, up to about 1600, it was not clear to people that floods were caused by extreme rainfall. And it may look something like amazing, you know, because in the 2000 years ago, there were scientific disciplines where people made really massive progress in understanding also nature. Think about the stars, think about several other things. But regarding the water cycle, it was precisely around 1600 that a monk in Italy realized that the level of the Trasimeno Lake was driven by the intensity of precipitation in the past weeks. He made observations and proved that. And you may wonder what was the previous explanation of floods. The previous explanation was water surging from the underground. And why is that? You may say, because in the past people didn't have a lot of connections and a lot of communication. So think of people living in the downstream part of the Po River getting flooded without any rain because it rained over the Alps and they didn't know that. Just to explain to you that for some scientific disciplines, they are really in their infancy. And so we understand why also collecting data started quite late. Data collection started quite late. And this is an example very long time series, sorry for the caption in Italian, which is rainfall in Bologna. This is a daily record. Here you see the annual values, but it's a daily record. This is like a treasure that we have here in Bologna. This is publicly available on the web. It's like a treasure because, can you imagine, more than 200 years, now it's already 210 years of daily rainfall, of course with zeros, but every day we have the observation of rainfall with very few missing values, very, very few. And it is interesting to look at the progress. And in this particular case, I looked at annual rainfall. This is made by me, but you can do it, it's on the web. This is the graph of annual rainfall with highlighted the long droughts. Why? Because I'm getting more and more concerned that in Italy may happen what is happening or what happened already in Australia recently from 2000 to 2010, in South Africa from 2013 to 2017, in California from 2015 to 2019. Which is a long-term drought. What is a long-term drought? It's a long-term shortage of precipitation that lasts for, like in Australia, it was 10 years. I'm getting more and more concerned because why shouldn't it occur here? Why? And so I decided to look at the series of precipitation in Bologna. It is a very quick analysis, just for looking at what happened in the past. And with the gray band, you see periods that occurred in 1800, and the last one was between 1940 and 1950, where rainfall on average was more than 20% less for 10 years. So what if a similar situation occurs now? It's a disaster. Because in 1940, it was an issue, but still, the water demands were so low if compared with today's one, which we could survive easily. But if it occurs now, it's an issue. So this is why I built this graph, and I'm now making research on that. What is the reason why, even 100 years ago, at a certain point, you get less rainfall and it may last for 10 years? And this is a treasure. By the way, I forgot that in a previous slide, I had a figure that I didn't comment. So let me go back a few slides before I make the break, because this is related to these cycles, to these extreme events that last for a long time. Let me go back just a little bit to the first slide, actually, here. Here is a picture of what happens with El Niño and La Niña. On the right, bottom right. You heard about El Niño for sure. What is El Niño? Is a large-scale atmospheric pattern, which means that in the atmosphere at the large scale, there is a process that starts a cycle that may be self-reinforcing. And this cycle so lasts for a long time and has the capability to shift rainfall from one region of the world to another region. So what is El Niño? El Niño, here the picture is related to La Niña. So if you look at the picture, you have to think at warm exchange with cool. And if you look at this picture, on the east of it, there is the west coast of South America. And in the west part of the picture on the left, there is Australia. So El Niño is a warming of the ocean, of the Pacific Ocean, close to South America, a warming which implies a cooling in close to Australia. So the warming in South America is self-reinforcing because we are not looking at the details. But if you go in Wikipedia, there is a nice explanation of El Niño. It's not a matter for the exam. This process is self-reinforcing. So it stimulates a circulation of the ocean currents that tends again to warm up the Pacific close to South America. And what implies a warmer ocean? It implies evaporation and then rainfall. So you get floods in the west coast of South America and droughts in Australia. El Nino, as I said, is a cyclical phenomenon and has different strengths. But it's impossible to predict when it will occur. On average, it occurs every, I think, 15 years. I don't remember. In my slides, there is written the average frequency. But we cannot really predict if it will happen next year or in 2 years. And La Nina is the opposite thing. Drought in South America, floods in Australia, and we cannot really predict it. So we know that there is this large-scale pattern. We see that floods in certain regions of the world and droughts in other regions of the world are related to atmospheric indexes, like difference in temperature between the West and the East Pacific Ocean, but we cannot predict when it will occur. And is the frequency of El Nino related to global warming? There is no final conclusion by the scientific community about it. Let me go back to rainfall in Bologna. Here it is. So, what happened during these droughts? This is an exciting question. And just to give you, to complete the picture, given that I am concerned, I looked at the prediction of climate models for the future, and we consider 13 climate models from the latest generation. And unfortunately, they don't predict so relevant droughts in the future. But I say unfortunately because the fact that it's not predicted by a climate model is not a good reason to forget about this possibility, this risk. If it occurred in the past, why shouldn't it occur now? It is very rare because you see that from 1850 to 1940, nothing happened. It's something that happens maybe every 100 years, we don't know. But given that about 100 years, or 80 years passed from the last time, who knows how long this drought that we are experiencing now will last? And what if it lasts up to 2027? It's a disaster. So how can we increase our knowledge of the past? How can we increase our amount of climate data? We will continue this discussion in the next hour after the break. Meanwhile, I forgot to ask you if you have any question, but you have to raise your hand if you have any question, or if you are attending online, you have to step in. Do you have any question? Okay, thank you very much. And let's meet again in 15 minutes.
Ok, amo 15 minuti di pausa. Dimmi,
Thank you.
hai trovato il phone?
Okay, let's restart. And let's restart with something that is a bit relaxing. I mentioned to you, not to you really, but it is written on my description of this course that we may dedicate some time to practical exercises, which is not easy because we don't have so many hours. But given that this year I am teaching most of the lectures, I thought that it may be interesting to have a look at some practical computation. And it is something that it is particularly interesting given the interdisciplinary character of this audience of you. And I make reference to the webpage which I am following to give this lecture. Let me go back to it. No, this is not the webpage. Here it is, where you can find a box with a very simple exercise, computation of statistics and use of statistical software. Let me just increase here the font. Before we look at, this is a very simple exercise. I mean, it's a plot of a series of temperature data in a very short series. But before we make it, let me just make a premise, which I think it is necessary because indeed the audience is interdisciplinary. When we have to analyze data, and data analysis is the basis for climate science, data analysis in terms of observation or future predictions. When we analyze data, there are several software, several methods that we can use to that. And for instance, I think most of you know Excel, which is a spreadsheet, which allows to make computations in a systematic way, systematic computation. Excel is a spreadsheet that is produced by Microsoft, but there are some clones which are public domain. Clones means, public domain clones means that, you know, Microsoft, you have to pay the license for Office, for Windows and Office to use it. The public domain software can be freely used. Excel has pros and cons. First of all, as a spreadsheet, I think is still the best one. It's much better than its clones. It has some limitations, and also the cons, the pros is that the advantage is not only the fact that it's very efficient, but it's also a software that allows you to see what you're doing, because you write numbers on the screen and you see the numbers there, and also you see the data. You can write something close to the data to explain what the data are. So it is a kind of what you see, what you get software. It means that you see what you are doing. The disadvantage of Excel is that this feature of what you see, what you get is paid back in terms of computational efficiency. So Excel is not very efficient. What does it mean, efficiency? It means the max number of data that you can analyze. So one thing is to analyze 10 numbers. One thing is to analyze 10 millions of numbers. And efficiency means also the velocity, the speed of the computation. When you manage many numbers, many data, we are talking about climate data today. When you manage long time series, the time required for making a computation may become excessively long. And the reason for this inefficiency is precisely that a lot of computational resources are dedicated to render, to show to you what the software is doing. So what is an alternative? The alternative to this kind of very user-friendly software is to use software that are more powerful in terms of efficiency, in terms of capability to manage numbers. But in order to be more powerful, given that the computational resource of a personal PC is anyway limited, they need to dedicate less resources to visualization. Visualization, interaction with the user is more difficult. You may have heard or you may have used MATLAB. MATLAB allows you to make similar things with respect to Excel, but it's less user-friendly and it's more efficient. Now, why I am talking of these features? Because, as I said, climate science deals with data, and I think that even if you probably, not sure, but maybe that you will never have the necessity to analyze climate data yourself, I think it is interesting that you get information, not for the exam, because this is not a subject for the exam, but you gain information on how these data, these numbers are crunched, how they are analyzed and digested. Finally, let's divide the softwares that you can use between, I already made this distinction today, between open source, public domain and commercial. Okay, and then open source is a different story. Let's focus on public domain, which means that they are freely available on the web, and commercial, which means that you have to pay a license. It's not just the problem, the fee, the license fee. This is in itself maybe not a huge problem, but keep in mind that some softwares, some commercial softwares may be very costly. And there might be alternatives that are public domain on the web. But it's not just a matter of the fee, it's a matter of accessibility and communication. So a software which has to be paid, no matter the amount of the fee, is less accessible. So in terms of equality of opportunities, diversity and inclusivity is a limitation, even if the fee is very low. And you may have heard that today, in the context of environmental sciences, the so-called EDI principles, equality, diversity, and inclusivity, and the initials are EDI, is given a lot of value, maybe in some cases even too much, because they are really overemphasized today, these principles. But on the other hand, it's clear, it's undeniable that equality, diversity, and inclusivity are extremely important, especially in terms of accessibility, in order to make, if we really want to promote a global effort. A global effort cannot be promoted by working only on our own desk. We have to be open. So if we use an open software, a public domain software, communication is much easier. Everybody that has a PC, or have access to the web, can communicate with you. This is why I am a fan of open teaching, open everything I said, okay? So when it's possible, I really hope that climate science is dealt with by using public domain software. So if we want to use a spreadsheet, can we use, is it some open domain spreadsheet available? The answer is yes, but today we are not focusing on spreadsheets. But yes, there are free and public domain spreadsheets available. You may have heard about LibreOffice, or there is also a GNU spreadsheet whose name I don't remember. There is to say, I want to be very clear on that, as I said, in my opinion, in terms of spreadsheets, Excel is still the best one. And also in terms of word processing, I think Microsoft Word is still the best one for the day-to-day use. But if we want to use open spreadsheets, there is the opportunity. Now, if we instead want to crunch several numbers, a huge number of numbers, if we want to analyze very extended big data, you know, big data is very popular today, and we have some branches of climate science that can rely on big data. They cannot go back much into the past, but think of satellite observations at the global level of clouds movement, clouds displacement, soil moisture, sea level elevation. These satellite images have a resolution that is very, very fine, and they produce every day tons of data. So we have indeed some branches of climate science that need to analyze huge amount of data. So if we want to use a computational software, not a spreadsheet, that is very efficient in terms of data analysis, are there alternatives to MATLAB, for instance? Yes, there are. And some of them are really competitive. So I cannot really say if there is a software that is better than MATLAB, but I can for sure say that for what my needs, I don't need to resort to MATLAB. I may need to resort to Excel, but not to MATLAB. So I want to make this simple exercise by introducing to you a data analysis software, which is public domain. In my opinion, is relatively easy to use. It's similar to MATLAB. It is more difficult to use than Excel. But on the other hand, I think that whatever your degree program, whatever your background, I think it is a useful information. So I think we can dedicate some minutes to see. And once again, this is not for the exam, okay? So what is the software I am referring to? It's called R, and there is a link in my webpage in this box. So what is the box? It's along the webpage of the climate change problem of this link. There is this link to the software. Let's click on it, okay? Here is, you see statistical computing, but this is a software for computation, not only for statistics. And by the way, statistical analysis in climate science is an essential piece, okay? But it's not really only for statistics. This software allows you to make very nice figures, for instance, which it is something that is relevant to you. If you really want to enhance your communication capabilities, being able to plot nice figures like you can do in MATLAB or you can do in R, it's important. And let me give you an example. Let's go back to my web pages, okay? 1 second, I am not yet there. Okay, it was here, sorry. Let me open another window. Too large. Science of climate change and climate action. Let me click just for a while on the next one. It's the climate change and water cycle. Let me scroll down just to show you a figure. This figure was done in R. And it's a representation, a 3D representation of the Po River flows to show the cycles, the seasons. It's an animated GIF. It was done in R, in this software by me. So if I could make it, it means that it's quite easy to be made, okay? Good. Let's forget about this for now. And also, I can close this window. Let's go back to R. This is the R website. You can find it in Google by writing R project with a slash, so Google. So if I go in Google and I search for R project, the first link I get to it. Now, we need to download and install it. Everything is free. How to download it? We have to click under download here, CRAN. CRAN or CRAN is a repository, a public repository of open source software. It's not easy to publish something there. everybody who produces a software and would like to make it openly available can submit the software to CRAN, and the software is then reviewed. And if it passes the review, it is accepted and published. This is one of my next targets for fun. I really would like to make this attempt to publish on CRAN. And keep in mind that people that are working in electronics or informatics, if they get published in CRAN, it's a good piece of the CV. But this is just for your information. So if you click on the CRAN, you have to select a mirror. Usually I select the first one, okay? And then you see that there is the download of R for Linux or for Mac or for Windows. You select your operating system. If you are using a Mac, of course, you take the Mac one. If you are using Linux, like I am a fan of Linux, why? Because it's open. Or you can download R for Windows. If you download R for Windows, you are given another option. We have to download the base. And then we get here again, next click, download R for Windows. And you get an executive file. You see, it's downloading. And then once it's downloaded, I am working on Windows now, you click on it and you get the installer. You see, select the language. By the way, here it's already installed, so I don't move forward now. But it is very easy. You just have to accept the defaults and you get at the end with the success story, and you get an icon in your list of application in Windows, R. And if you click here, you see there is R 4.2.2. And if you click here, you get to R. So R is this one. Let me just increase the fonts, okay? Preferences. Unfortunately, I downloaded it in Italian, but I think that you can be patient with me. This is R. And R is not really user-friendly for the reasons that I mentioned to you. So it's a command line based software. What does this mean? You don't have to work with the mouse or with menus, even if you see some menus here, but let's forget about them because it's not conceived to work with menus. It's not a user-friendly solution. It needs to work with command lines. I have to write what I want to get. For instance, 2 + 2 gives 4. If I press enter, gives 4, surprisingly, okay? Or I can write a = 1, I assign a variable, and then I can write a × 2 and type enter, and it's 2, okay? So I need to know the language. Learning the language is not easy. For instance, I had to know that it can accept simple computation like 2 + 2 from the keyboard. This is not really something to be taken for granted. So you need some training, which is not very demanding, but still it's needed. And in the website, our project, there are also tutorials, very short ones, which you can learn. Now, let's make the exercise that it's proposed on my webpage here. Okay, first of all, I clear the screen. Okay, Control-L, but let's forget about this instruction. If you are interested in learning the software, this is an independent activity that you have to undertake on your own. Okay, I can give you some advice if you want, but this is an independent activity. And let's go back to my webpage and see how to make the exercise. And what we have to do is just to make a cut and paste of the instructions. So we don't have to learn the language. Let's make a cut and paste. It is very, very easy. Let me see, where is my web page, because I think it's here. Good. So you see, what I just need is to copy this instruction. Let's forget about the meaning. Let's make cut and paste. So I selected it on the web, and then I right click, copy, and then I shift the window. I go into R. Here, right click, paste. So I defined a vector through this instruction. Let's write this vector on with the keyboard, and I type enter. You see that I have this vector, which is supposed to be a temperature series. The exercise says that this is a temperature series, which is now stored as a vector. You know what is a vector? Is a cluster of numbers. Now, what is my purpose now? To write, to show, to build a plot of these numbers, like it is shown here. Okay, so let's again copy and paste the instruction. Copy. And let's paste it here. Paste. This is the graph. So you see that let's go back to the instruction. It is very simple. Plot temperature, X label days, X label, Y label, daily max temperature, type bold, type both. It means both line and points connecting the numbers. Colors red. And this is what I obtained. Good. Furthermore, we are also done. We can compute basic statistics like the average, mean of the vector. Copy, paste, just 1 second. I have to go back to the console. And paste, mean, temperature. This is the mean of the vector. And other statistics like standard deviation. What is standard deviation? It is a measure of variability of the numbers. So SD temperature. This is the standard deviation. Again, it's a measure of variability, of fluctuation around the mean. And it is interesting in climate science because variability, as we know, it's important. Okay, I stop here for now. Let's close the software, and you may want to save it or not. So for closing, it's Q and then 2 round parentheses. Do we want to save? Let's say no. I'm not interested in saving, and we are done. I think.
Excuse me, I have a question if I can interrupt. Sorry. Would, for the purposes of this class, we be able to also use RStudio, or is that not enough?
RStudio is you're moving a step forward. So during this class, we will not use RStudio. RStudio is an interface that allows you to dialogue with R through menus, and it allows to put together in the same screen several plots, several windows. So it is free. You can install it, but we will not use it during this class. And I tell you, we will not use computation much during these classes. I will use computation just to make a break, to make the lecture more diverse, and I hope you appreciate it.
Okay, thank you.
Yeah, no problem. And when I make these attempts to make the lecture more diverse, I am aware that the audience is very diverse. So for some of you, these are trivial concepts. For other of you, this is something too complicated. This is normal. It's interdisciplinarity. It's why it is not easy to be interdisciplinary. But in order to be interdisciplinary, you have to make an effort also to learn the things that are more hostic, more hostile. And you have also to make an effort not to give for granted any knowledge. When you talk with an audience, if you want to be understood, you have to be very clear, very understandable. Good. Let's go back to our PowerPoint presentation. And to this time series, we are talking of data, so it's extremely important to understand how we can analyze data. So We may limit the problem of the limited extension. We can mitigate the problem of the limited extension of the climate data by using reconstructions of the past climate. And the really interesting information is provided by the proxy data. Proxy data are not climatic data, but are data that are related to climate, which can be used to estimate the features of the past climate. The most interesting example is given by tree rings. Tree rings give us a picture of the far past, not very far, but for hundreds of years, yes. Okay, for several hundred of years. And this is an example. Another example is ice core data. If we drill a carrot of ice in the polar caps, there is a lot of research on that. Then by looking at the layers of this carrot, we can understand several features like the intensity of precipitation, or if we look at the isotope composition, which means the isotopes that are trapped into the ice, or the dust that is trapped into the ice, we get information on the past behavior of rainfall, because precipitation and snowfall and rainfall are bringing isotopes taken from the atmosphere to the ground. They are bringing dust taken from the atmosphere to the ground. So for instance, past volcanic eruptions can be dated through the analysis of the dust depositions in the ice cores. This is extremely interesting. And also the tree rings, if they are thicker in some particular years, it means that during that year, the tree grew up more, which means a climate that is more favorable to the growing of vegetation. What is the problem with this data? It's, of course, uncertainty, because they are not directly related to temperature. We need to calibrate them. So we need to look at the tree rings for the instrumental period when we have temperature data, and study how the temperature data that we observed from 1850 to today are related to tree rings. And then we extend to the past this relationship to reconstruct past temperature. But of course, you know what is extrapolation? It means that you get a known information and you extrapolate this information to cover a domain which is not known. Extrapolation involves uncertainty. Okay, so there is uncertainty, and there is the problem that these data usually provide information at annual time scale, not at seasonal time scale. So the tree rings data, they give an indication of annual pattern, not not intra-annual patterns, not seasonal patterns. Okay. But nevertheless, they are very interesting. I want to give you an example. I have a PhD student now that is working on trying to reconstruct the flows of the Po River. And what he's doing, he has access to a bank of tree ring data for the long past. And now he's studying the correlation between the observed river flow, the Po River, from 1920 to today, and the thickness of the tree rings. And then he's in charge now of finding the good combination of tree rings that are well related to the Po River flows. The problem is that the tree rings, the bank of the tree rings, is particularly rich only for some regions of the world where the secular tree grow up. So for instance, in Italy, there are very few of them available. Also because, you know, to analyze the tree rings, you need to cut the tree. And this is not easy. So of course, it's something that you can do if you have a lot of trees, and then some of the trees die, and then you study the tree rings. But if you have only a few trees that are multi-secular, and you cannot cut the tree for the purpose of scientific research, of course. And therefore, he has a few 3 rings data available for Italy. So he's trying to connect with 3 ring data that refer to the north of Europe. And this is a bit challenging because the correlation of the 3 rings in the north of Europe with the Po River flows is very low. But he's managing to find a good combination because we have to put together information from several trees, not just one, to minimize uncertainty. And the aim is to extend the Po River flow up to 1,000 years. Why? To study droughts, simply. So you don't need really certainty, but you need something that is reliable. Because to estimate droughts, you know, even if you have uncertainty, anyway, what you need is information on the number of years, number of events in the past where for several years precipitation, so tree ring growth was lower than average. So you don't need really much uncertainty. You don't have to design a dam. So for this purpose of scientific research, even if there is uncertainty, we can afford it. But of course, it's not easy to find the right combination of trees. I think it's an interesting example of what we can do with, in order to extend our knowledge of the climate of the past. So we have another solution that can be used in order to understand past climate, and is the use of models, mathematical models. So once we understood the science behind climate, we can apply, for instance, conservation laws to study the dynamics of climate, the evolution of climate. This is useful for studying the future, but it can be used also to study the past. And therefore, models are another opportunity. What is the procedure for building a model? We will have a lecture on climate models because I think it is extremely interesting to understand how they work. But the procedure is, first of all, to devise a theory. So you have to set the theoretical basis. You have to gain an idea of how it works, the system that you want to describe. For instance, if I want to estimate the time that is taken by this object to drop over the floor, I need to make a preliminary elaboration, perception of the theory, like the drop is driven by gravity force. I know gravity force, and so let's see if my theory can explain the time taken by the object to drop down. This is what Galileo seems to have done by dropping different objects from the top of the Pisa Tower. It seems that if it's true, because you know, sometimes to distinguish the myth from the reality is not easy when we talk about big personalities of the past, but it seems that he made experiments to explain gravity by dropping objects from the top of the Pisa Tower. Now, so I have to elaborate a perception, and then what I have to do is to write an analytical model explaining the drop of the object. So if it is gravity, I know that I can write a formula to compute the acceleration along time. And we know that acceleration is constant, it's gravity, but the velocity is linearly increasing with time. So if I multiply acceleration by time, I get the velocity. And then I can derive the time taken to drop on the floor. We are not computing it now, but this is gained by my perception of the theory. And then I have to make experiments. So I try to measure the time taken by dropping the object, and I check whether the theory can explain what I observed. Okay. Now, I know gravity, but in some, I may also use the same approach even if I didn't know the value of gravity. If I understood that there is indeed a driving force, which is gravitational attraction, that governs the drop of the object, I could test whether this model, even if I don't know the value of gravity, works how can I make it? I can just make several experiments to compute the time taken by the object to drop down. And I see that the time is constant, more or less. And this is what Galileo did. He basically dropped several objects with different mass from the top of the Pisa Tower. And he realized that the time that the object took to reach the ground was independent of mass. So I see that the time is constant, and then I can write my model with the gravity as an unknown, and I can estimate the value of gravity by estimating the unknown. So if I know that the time taken is 1 second, I write my mathematical model with the gravity as an unknown to compute the time. And then, given that I know the time, the only unknown is gravity. I can estimate the gravity. So even if I didn't know some features of this process, of this dynamical process, I can calibrate the model to get information on these unknowns, optimize the model. Okay, you may say, yes, but in doing that, you basically are not sure that the model is correct, because your calibrated parameter may compensate for something wrong. That's true, that's part of uncertainty. So this is just to say that when I want to explain a complex process, I may also accept that some part of the process are not known. Not in this case, when I drop an object, I know the gravity. But even if I didn't know it, I could estimate the gravity by measuring time, which means that I can also use the model to gain a knowledge on the process. This is why models are also learning tools. What is the moral of the story? Climate models have several unknowns. So I make a theory, and then I calibrate the model by looking at the observations, and I try to estimate the unknowns, like maybe, for instance, contributions to climate of CO2 emission, greenhouse gases, by optimizing the simulation, by finding the best value of the unknown that makes the simulation more reliable. And then I can extrapolate in the future and in the past. This is the philosophy of modeling. There is uncertainty, yes, because we don't know everything about climate. There are some drivers which we still don't know. But I just wanted to mention that in order to compensate this limited knowledge of climate, we can use proxy data, we can use models. And indeed, we use models to make predictions. Let me just see if there is a next slide. No, this is the last one. We have just a few minutes to go. Let me mention something related to climate impact in order to close this lecture, to provide another evidence of climate change. The figure that you see here is reporting losses from weather disasters worldwide in 2000, from 1980 to 2019. Look at the top figure. Just forget about the lower one for now. These are losses from weather disasters. There is a clear increasing trend with some variability, some spikes, but there is an increasing trend. These data are provided by Munich Re. It's an insurance for insurance company. What does this mean? Insurances, we know what they do. They work to basically give a compensation, a monetary compensation if we are damaged by a certain risk. So for instance, well-known solutions to mitigate the impact of climate change is insurance. Like if I realize that I am exposed to a risk of flood that is increasing, a possible solution is that I get an insurance paying back for the damage if I get flooded. The same for droughts, For instance, the farmers are used to get insured against the occurrence of droughts. Now, for the insurance company, of course, it's their business, but on the other hand, they need to get insured because they cannot accept the risk of default if something really wrong happens. And they are also compelled to get insured. So there are insurance for insurance companies, which their job is to provide insurance to the insurances. And one is Munich Re. Munich Re does a lot of research on climate change because, of course, their job is quite delicate and they have to study the extremes because, of course, their service, their insurances cover only the very rare risks. The insurance company don't get insured against the day-to-day accidents. This is not a problem for them. They get insured for the accidents that can break the company out. And therefore, the very rare ones. And Munich Re has to cover these very rare events. So they do a lot of research and they put the data available. And this graph is using open data, which I downloaded for the Munich Re website. There is a link there. So let's go back to the problem. There is a clear trend, but on the other hand, if you divide the damage by the global gross domestic product, what you get is the lower graph, which is not so trendy. What does this mean? When you consider the impact of climate change, you have to be aware that it can be caused by several drivers. One is climate change itself, and the other one is the GDP of a country, because an essential element of risk is the value of the damage that you get, the value of the land, the value of the assets that are damaged by climate change. If the value is higher, you get a higher damage, you get a higher impact. And therefore, we have to be fully aware of the complexity of the problem. So today, basically, we talked about the complexity of the problem, interdisciplinary, uncertainty, several drivers, and we talked about data, which are essential in order to understand this complexity. And then next time we talk about the models. Questions? Let me stop the screen sharing and the recording.